Okay, good morning. Good morning to all of you.
Good morning, sir.
This call is now being recorded.
Okay, am I audible?
Yes, sir.
Yes, sir,
Okay,
audible.
so okay, so we can start. Just wait. So can anybody tell where we left in the last class? Probably we have started chapter 7. So how far we have proceeded? Can anybody say? So we can start from there. Have you remembered? Yes. Why are you keeping quiet? Just wait. Is this deletion plan? What is deletion plan? So I think this is chapter 7. So let me copy this one. See. Okay. Okay, so now here we are. So yes. So tell me where we left in the last class. Yes, anybody? Anybody? Saurabh or Asutosh Ranjan? Can anybody say where we left in the last class? So that we can start from there.
Yes, I'm telling.
Hmm?
We did the three cases. The three cases where work done by other forces is equal to zero, and then that is
Okay.
greater than zero.
Okay.
Yes, sir.
Okay. Right. Okay. So probably we'll start from the conservative and non-conservative forces anyway. Okay. So what we did in the last class, you see, we found out in chapter 6, actually, let me tell you, in chapter 6, actually, we learned about one theorem that is very important, work energy theorem, isn't it? Work energy theorem. This theorem says that, what this theorem says, that the total amount of work done, okay, the total amount of work done, W total, this is total, the total amount of work done by all the forces present is equivalent to delta K, isn't it? Change in, this is work energy equivalence principle. Okay. So how many forces will be there? If each forces will be doing work, and if you add all the work done by all the forces, then you will get the total work done. And that total work done, if you want to calculate it, just look at the changes in the kinetic energy, and that will give you an idea of how much amount of work is done by all the forces. Okay, so that is work energy theorem. In chapter 7, we learned another important thing, that is, if there is a force like a gravitational force which is a constant force, and that is the only force present, then the work done is equal to, this work done will be equal to, you see, this work done is equal to minus change in the potential energy. That is a very important thing, minus change in delta uz. Okay, delta u, and this GRAV. This GRAV is the gravitational potential energy. This we learned. This is a very important expression, particularly this negative sign. This negative sign is very important, and this is also W grave. So let me write it, because the work done by the gravitational forces, you cannot write this thing for all kinds of forces. So work done by the gravitational forces is equal to minus delta U grave. Then what we did, suppose the only force present is the gravitational force. Then you can write W total is equal to W grave, isn't it? Then you can write W total is equal to work done by the gravitational force, that you write. Okay, sorry, this is, oh sorry, this is grave, GRAV. So this is also GRAV. So W total is equal to the work done by the gravitational force. Then if we, because we have found out W total to be equal to delta K, so I can find out delta K is equal to minus delta U grave, minus delta U grave, isn't it? That means this is also a very important conclusion, that the increase in potential energy is equal to decrease in the kinetic energy, or vice versa. Or you can write this equation as, from there you can bring this minus to this side, isn't it? So it becomes plus, and then the right hand side will be equal to 0. Then what you will do, then you can take a delta, okay, and show the change in kinetic energy plus change in potential energy, gravitational potential energy, must be 0. Or you can write, put a bracket here, okay, and then you can find out this, see, you can put it here, okay, and then so K plus U grave, and then you can remove this one, isn't it? So delta K plus U grave is equal to 0. So and this K plus U grave, which is there inside the bracket, this is equal to another new thing, and that is what is called the mechanical energy. Okay, mechanical energy E, the total mechanical energy. So I can write my equation as this equation can be written as delta E is equal to 0, isn't it? Because delta E is equal to E2 minus E1, so I can write this equation as this delta E equation, I can write it as control V. So this I can put a E2 minus E1, isn't it? So this becomes E2 E2 minus E1. E2 minus E1, this becomes E1 is equal to 0. Or you can write, that means change in the total mechanical energy is equal to 0. So there is no change actually. Or you can write E2 is equal to E1. That means the total mechanical energy remains conserved if only gravitational force is present. Because E2 is equal to K2 U grave, so you can also write this equation as K2 U grave, you can write it as K2 U2 grave. Okay, so you can write a 2 here and a comma, or that is equal to, that is equal to K1 U1 grave. U1 grade. Okay, that means if only gravitational force is present, remember this thing, if, because we have found out this conclusion, assuming that the only force present is the gravitational force. So when gravitational force is present, then you can conclude that the final kinetic energy, sum of final kinetic energy plus final potential, gravitational potential energy must be equal to sum of initial kinetic energy plus initial gravitational kinetic energy plus initial gravitational potential energy. That means the total mechanical energy of in a system where only gravitational force is acting remains constant. That is the conclusion that we are going to get, and that is what is called conservation of mechanical energy, total mechanical energy. Your kinetic energy is not remaining conserved. Your potential energy, gravitational potential energy also not remaining conserved, but the sum remains conserved, and that sum is called the total mechanical energy. This E is called the total mechanical energy. Okay, this E is called total mechanical energy. Okay. Now, naturally, a question arises in our mind that what happens if other forces are present? Can we write this conservation equation when other forces are present? Now, before going to that, let me tell you, like this gravitational force, which is for which there is a potential energy function. Similarly, there is another force which is called an elastic force. And so, but that elastic force is variable. And can we find out the same equations for an elastic force also? So you see there is another force which is called the elastic force. So in place of this gravitational, I can write this elastic force, which is also a variable force. And you know the equation, how this F elastic, F is equal to minus Kx. So this is the force, elastic force. You can write it as F is equal to minus Kx, isn't it? So this force, this elastic force, is a variable force. But here you see, here we are dealing with, when the gravitational force we are dealing, that force is a constant force, isn't it? If you can write it, if I will write this as F elastic, also I can put a symbol and I can write it as F elastic, isn't it? To signify this force as F elastic is equal to minus Kx. So similarly, here this gravitational force also I can write it as F gravitational, F GRAV is equal to minus mgy, minus mgy. Now you see this gravitational force, which is a constant force and is the only force present, then we see that the total mechanical energy remains constant. Similarly, when elastic force is present, which is a variable force, this is an example of a variable force where the force is not remaining constant, variable force. Here this is, we are dealing with a constant force. Okay, this is a constant force. Okay, this is a constant force and the other one is a variable force. Even for the variable force, we can find out that the work done by the gravitational, as this is the work done by the gravitational force, I think I have also found out these equations for you. Also, if I found out that W elastic, I can find out as elastic potential energy. This is an elastic potential energy. And here you see this U grave, isn't it? This U grave can be written as mgy, isn't it? That is important. So this U grave, you can write it as mgy. This is the gravitational potential energy, isn't it? Oh, sorry. This is, are you, whether you are you listening me? Are you there? Hello?
Yes, sir, listen.
But when I am
Yes, sir.
committing mistakes, why are you not pointing out? Because I have written this F gravitational is equal to minus mgy, but it is minus mg, and you did not point out the mistake. So you should be very careful. U gravitational is equal to mgy. How we have derived these equations, I have probably shown you. Why? Because for a falling body and for a, of course I can, if you like, I can show it once more. Similarly, we have found out that work done by elastic, only when only force present is the elastic force, then the work done by the elastic force is equal to minus delta UL. Now, by the same logic, you can derive the whole thing and you can get out this thing, isn't it? Because your potential energy can be of various types. If a gravitational force is acting, that is called gravitational potential energy. If an elastic force is acting, that is what is called an elastic potential energy. Now you see, when only elastic force is acting, then your total work done is equal to work done by the elastic force. And delta K, if now it becomes equal to delta U EL. And all this gravitational will be replaced by elastic, and similarly you will get this easy. Now this becomes your total mechanical energy, potential plus kinetic, isn't it? So similarly you can write. Now you see the third example shows that suppose both the forces are present, elastic forces and the gravitational forces, then what I am going to derive? Suppose both the forces are present, the variable force is also present and the constant force is present, elastic force and the gravitational force, and the gravitational forces are present, then what will happen? Okay, now what will happen? Now your total work done, this W total that you have written, now this W total will become WEL plus W grade, isn't it? This is equal to W grade, because now both the forces will do work. The gravitational force will do work and the elastic force also do work. But W total is equal to WEL plus W grade. But W total is equal to delta K. You see, we have written W total is equal to delta K, isn't it? Have you not written it? WK is equal to delta K. So I will write W total is equal to delta K. WEL we have already found out. What is WEL? WEL is equal to minus delta UL, isn't it? Minus delta UL. Minus delta UL, and W grave is equal to this W grave. In place of this EL, I will write GRAV, and similarly here I will write GRAV, isn't it? So now I can write minus my delta K. If I put it in this first equation, then I will get delta K is equal to minus delta UL. So very beautifully you can find out lot of things. Then delta U grave, isn't it? So delta U grave. Then little amount of algebra that we have to do. What is this algebra? So just a little amount of reshuffling. I will take this minus common. So I will put a bracket. Okay. And then I will bring these quantities inside the bracket. Okay. So I will bracket, and this minus will become plus. Okay. And then what will happen? Now you can see, I will write this delta. I will take minus and the delta common. Then the inside will become UL. So you see this will become UEL. Just I will write it as UEL. Oh, why this UL is not coming? Just wait, I can write it as EL U plus plus U grave, isn't it? And this is my U. And now this whole thing is nothing. I can repeat it. You see, now this UL plus U grave, I can write it as the potential energy, isn't it? See, delta U. So I can now take out the bracket and I can write delta U, and this bracket is no more required. Okay, so delta K is equal to minus delta U, where this U is equal to the total potential energy, isn't it? Where this U is equal to UEL plus U grave, the elastic potential energy and the gravitational potential energy. We will work out very nicely all these graphs also, just wait. So now again my equations, I got my equation as, you see what equations I will get. So I will get these equations. Now this will be no more. Okay. So delta K is equal to minus delta U, or delta K plus U is equal to 0, or delta E is equal to 0, or E2 is equal to E1. Like this, from whatever I have got from here, I can find out from all these things. From here I can find out the whole thing, isn't it? And I can write my conservation equation. So from here I can write delta K plus U grave. U, in place of U grave, I'll write only U. Then this U grave. Okay, I will write U. Oh, sorry. This is U. So the total mechanical energy bus. So K1 plus U1 is equal to K2 plus U2. That is how you can get the equation. These equations that I have written, you can get it like this, isn't it? So you can write that K2 plus U2. Now no more this gravitational things will be there. So K1 plus, oh sorry, K1 plus U1, isn't it? K1 plus U1, isn't it? Where U2 is equal to, now suppose I want to write it. What is my U2? When both the things are present, then U2 is equal to mgy2. mg y2, isn't it? mg y2, this is y plus my u1 is half kx1 square, isn't it? I can write it as half 1 by 2 1 by 2, k is the spring constant and x is the displacement from the mean position. So this is sorry, I will bring this one, just wait. So this is my square, this is my x, and this is my 2, half x2 square. Similarly, this is my u2. Similarly, my x2 will be control v. Here I will write 1. This become mg y1, and this 2 will become x1 square. Okay, so finally you will get that suppose you have got your mass v2, then how these whole equations can be written in the presence of both the forces? Both the forces, you can write as this equation as k2 is equal to half mv2 square. So this will become 1 by 2. Suppose it has mass m and it is moving with a velocity 2. So this will be v2 square. Just wait. So I will use this one. So this will be 2. This will be 2. This will be v. So half mv2 square, and in place of this u2, I'll write this equation, isn't it? I'll write mg control v, mg y2 plus half kx2 square is equal to, then that will be equal to the initial sum of the kinetic energy and the potential energy of the system. Now the system consists of two types of potential energy. So this will become your mg y1, and this will also becomes mg x1 square. So look at this equation. So this is the explicit expression of these equations, isn't it? This is how you will get. Now the next question is, what happens when other forces are also present besides this gravitational and the elastic forces? What will happen when what happens when other forces are present besides forces are present besides the gravitational and the elastic forces. What will happen? What happens? Okay, let us inquire. Now what will happen? Now this W total that you are writing, you can start from here, isn't it? The whole thing can be repeated. Now you have to add another thing, WEL plus WE grave plus W other, isn't it? So you have to write a other. The other forces will also now come into picture. Okay, so as usual, you can just repeat the whole thing, isn't it? Now this W total, you can start repeating all these things, isn't it? And finally, what you are going to see. So where there will be corrections, I will correct it. So what I will write? So W total is equal to delta K, that is right. WEL is equal to minus delta UL, that is right. W grave is equal to minus delta U grave, but I cannot associate, that is very important, but I cannot associate a potential energy function for the other forces. That is very crucial, and that will actually bring us to this unit 3, where we have discussed about conservative and non-conservative forces. Because you see, sorry, this is this W other, you cannot express it. You cannot express this W other, you cannot write it as a function of any delta functions. You cannot write it, isn't it? So that is the crucial point. You cannot write it like this because your frictional force is not associated with a potential energy function. So you cannot write W other with a potential energy function. So now your delta K, you have to keep this W other as it is. Okay, so I am going to keep it as it is. So W other will be like this, isn't it? And so everywhere delta K and then this W other will be there. So you have to add this W other to your equations. So delta K, I will add it plus W other. Similarly, change in kinetic energy, W total delta K is equal to W other. So here also I will add it as W other. So delta K here also I will add it as W other. Here also I will add it as W other. Then U is equal to this one, but delta K is equal to here also I will add it at W other. So here also I will add it, or delta K plus delta U is now is not equal to 0, but that is equal to W other. So this is what actually I am getting. Now, so this or delta E is equal to, you can write is equal to W other, isn't it? K plus U is equal to total mechanical energy. That part is okay. So delta E, but delta E is equal to W other. So that is important. So E2 minus E1 is equal to W other, isn't it? Or E2 is equal to E1 plus W other. Okay. Okay. So W or W other. So E2, now depending upon this W other, what is W other? Now you see, if W other can take three values, it can be equal to 0, or W other can also be greater than 0, isn't it? It can be greater than 0, or W other can also be less than 0. This can be less than 0. Now you see, when this W other is greater than 0, then E2 is greater than E1. That means the other forces have done work on the system. That's why the total energy has increased. If W other is less than 0, then E2 is equal to E1 minus W other. That means the final total energy is less than the initial total energy, because the system has done work through other forces on other systems. When W other is equal to 0, there are no other forces present, so the final total mechanical energy is equal to the total initial mechanical energy. So this is how we have discussed about almost all things. When other forces are present besides the gravitational elastic forces, what happens? When only elastic forces are present, what happens? When elastic and gravitational forces are present, what happens? And when only gravitational forces is present, what happens? So I think we have discussed everything threadbare. And I hope we have also worked out test your understanding 7.2 and example 7.7, isn't it? So now we'll go to the next topic, that is conservative and non-conservative forces. So because I have prepared the background, then now I will be in a position to discuss about conservative and non-conservative forces. Okay, so conservative forces and non-conservative forces, as you see, the work done by a conservative force always has 4 properties. If you have looked it correctly, otherwise I will also show you, just wait. So, are you able to listen to me? All of you? Hello?
Yes, sir.
Yes, sir.
Okay. Okay. So,
Hello, sir.
now you see, yes. Have you got
Audible, sir?
any question?
No, sir. Audible.
Yes?
Your voice.
Audible, audible.
Audible. Okay. Now
Yes, sir.
you
Mic testing.
see, okay, so now this brings us to the concept of conservative forces, because now we have seen that at least there are two forces, one a constant force which is the gravitational force, and the other a variable force which is an elastic force, which are probably different from the frictional force, because the frictional force cannot be associated with a potential energy function. There is no U existing for a frictional force, but there is an U existing for a gravitational force, and also there is an U existing for the elastic force. What is the U that exists for the gravitational force? That is that is mgy. And what is the U that is existing for elastic force? That is half kx square. But there is no such potential energy function or U for any frictional force or any other force which is not conservative. So this speaks us, or this indicates that probably these gravitational forces and the elastic forces are conservative in nature. What is conservative in nature? That means when only gravitational forces are present, then the total mechanical energy is conserved. Similarly, when only elastic forces are present, the total mechanical energy is also conserved. So when both the gravitational forces and the elastic forces are present, then also the total energy is conserved. But when other forces are present, depending upon the sign of the other forces, your E2 will either be greater than E1, or it will be smaller than E1, or it will be zero when other forces are absent. This is so. Now there are four properties of conservative forces, and we will discuss everything very nicely. Just wait. So conservative forces. What does that mean? I will explain you everything. So they have four properties. What is the first property? It can be expressed as the difference between the initial and final values of a potential energy function. It can be expressed as a difference, as difference between two values. Difference between two values. That is how we can express it. Okay. Just make a small reversible. It is reversible. Okay. 3. Independent of the path. Path independent. Path independent. Path independent. I will explain everything. Just wait. And the fourth one is zero for cyclic path. Zero for cyclic. Zero for cyclic path. Okay. So conservative forces, the work done by a conservative forces. Work done by conservative forces have the following properties. Okay. So what is that I just want to tell you. Difference between two values. So let us go to this point. So you have seen, suppose first let us go to the gravitational potential energy. I will take gravitational potential energy as an illustration. So what is the work done by a gravitational force? I can write it as W gravitational is equal to minus delta UL. Okay, minus delta U grave, delta U grave. Okay, so let me write that is equal to, let us put minus, and then delta U grave means U2 grave, U2, find U2 grave minus U1 grave. I can write it like this, minus U1 grave. Okay, minus U1 grave. Now if I will open the bracket, then this will become U1 grave minus U2 grave. U2 grave. Okay. Then that is equal to, if I put the value, then this will be mgy1 minus mgy2. Okay, mgy2. So look at this equation. So, and what this property, first property say, the work done by a conservative force can be expressed as the difference between two values, the initial value and the final values. And that is what we have got. You see, this is the work done by the gravitational force. Because it is a conservative force, so we are able to express it as the difference of two numbers. This is the initial number and this is the final number. So difference of two numbers. So the first part is over. Now I will skip the second part and go to the third part. Okay, third part, path independent. What does that imply? Let us see. Now I will take you to a building. Okay, suppose this is the building. Okay, and you are standing here. Air resistance is almost nil, suppose. Okay, now I will ask you questions. You have got 1, 2, and 3 balls with you. Okay, at the same, from this height, you drop a ball like this. It touches the ground here. You allow the other ball to move like this and touch the ground here. And the third ball moves like this and touches the ground here. This is path 1, this is path 2, and this is path 3. So this will naturally, for path 1, I will write it as a W1, this is W2, and this is W3. Now, can you say which quantity is bigger, W1, W2, or W3? And all are the work done by the gravitational force. Okay. Yes. Are you able to see my screen?
Yes, sir.
Yes,
So,
sir. Yes, sir.
yes. Then what is the relationship between W1, W2, W3? A ball falls like
Sir,
this.
all are equal.
Touches the ground here. All are equal. Why all are equal? How can you express W1? You just tell me. Suppose I want to express W1, and I have to write a grave also like this, the work done by the gravitational force. Okay. How? So what should I write? Yes, tell me. You have to tell.
Sir, MGH.
MGH. Actually, you have to express this one. So the initial one is suppose YE, and the final, this ground is because 0. So Y2 is equal to 0. So that is the advantage you are enjoying. Y2 is equal to 0. So, and suppose Y1 is equal to H, because your friend is very familiar with that H from school probably. That's why he is using H. Good, there is no harm in this utilization, but you have to follow this logical structure. So because now in place of Y1, I will write H and Y2 is 0. So I will get MGH. Similarly for W2, same MGY1 minus MGY2. Y2 is 0, Y1 is H. So again for W2 also, I will get MGH. You see, MGH. I am getting same thing. And for W3 also, I am getting same thing. So it is path independent, isn't it? Provided what? Provided
Only gravitational forces.
provided the endpoints are same. Actually, I should have path independent if I should mention if endpoints are same. If endpoints are same. That is important. If endpoints are same, because you see the starting point and the ending point are same in all these three cases. That's why you are getting the same conclusion. So if the endpoints are same, then there exists infinite path for which the work done will be same. It is not going to change, provided the endpoints are same. Because why it happens? Because ultimately the work work done depends upon the two endpoints. You see, y1 is the coordinate of one endpoint, y2 is the coordinate of another endpoint. Because when you will write this equation, you can write mg is same. So the only difference lies here, y1 minus y2. So when the endpoints are same, then y1 and y2 are same for all the paths. So they are not going to depend upon the path, provided these endpoints are same. So that is very important. And this different, why they strike at different points? Because they strike at different points due to the horizontal velocity. Here the horizontal velocity is 0. Here it is little bit bigger. It is much bigger here. And if you still have a higher velocity, then it can touch here like that. All kinds of possibilities will be there. Okay, so that is the third point. And the fourth point is 0 for cyclic path. Because why it will be 0 for cyclic path? Cyclic path means the endpoints are same. Because if a object starts from here and come back to this position again, then the total work done will be 0, or work done by the conservative force will be 0. Why it will be 0? Because the endpoints are same. y1 will be same with y1. So mgy1 minus mgy1 will be 0. So for a cyclic path, the work done will be 0. And that is the example of conservative force, not for a frictional force, that you must understand. Non-conservative forces, they do not obey all these four properties that I have told you. Because for a frictional, if there is friction and if you take a longer path, then you have to do a lot of more work, isn't it? When you slide a box, and if you are taking different paths, suppose you are taking this path, you are taking this path, you are taking this path. So naturally, this path, for this path, you have to do least amount of work. And for this path, you have to do highest amount of work because there is friction. But if there is no friction and only conservative forces are present, then you need not worry about the path, provided the endpoints are same. That is very important. Okay. And it is reversible. It is reversible means the kinetic energy and potential energy can interchange, isn't it? Okay. So this is how these are the four properties. Now, is there any question on this? Let us find out. Texture understanding 7.3 and 7.14. 7.14 is not more. Okay, anyway, so no more questions. Only one thing is there, but that is not important, that we can discuss a little bit later. So I'll go to chapter 4 probably, law of conservation, conservative and non-conservative forces I have told you, and the law of conservation of energy, that we will discuss also. Let us discuss because we have got 10 minutes. So I think we should discuss the law of conservation of energy when other forces are also present, and both the conservative and non-conservative forces are present. Okay. what happens? The question, let me frame. What happens to the law of conservation of energy when both conservative and non-conservative forces are present? How we are going to write the conservation law? Okay. Now you see, it is found out that the work always in non-conservative forces, energy is dissipated. That is very important. Are you able to understand what I mean? Dissipation means, did you understand what is dissipation? What is dissipation? What is dissipation?
Don't know, sir.
Huh? Dissipation
No idea.
means loss. Okay, dissipations mean loss, LOSS, loss. Suppose a other force is present in the form of frictional force, and I am sliding a box. Let us assume. So what will happen? I am just telling you one thing. Just wait. So. Frictional force is present, and it's like air friction, suppose. Now common sense says you that when energy is lost or energy is dissipated, which becomes more, your final mechanic total energy or initial total energy? Yes.
Initial total energy.
Yes, initial total energy will be more because energy is lost in the process, because the frictional forces, the presence of frictional forces either in the form of dissipative forces or non-conservative forces. The presence of non-conservative forces either in the form of air resistance or friction always dissipates energy, or energy is lost, which we cannot regain, which we cannot get back. But that doesn't happen due to conservative forces. When we throw a stone and air friction, air resistance is not there, then we think that our kinetic energy has been lost. But no, the kinetic energy is being converted or stored in the form of potential energy. And when this stone will reach certain height and then while falling back, the kinetic energy that the stone appears to have lost will again come back in the form of kinetic energy. हमको वही kinetic energy we can again get back. But this is not the case with air resistance or frictional force. Once the energy is lost, means it's lost. So normally that's why we can say that the work done by other forces will be a change in internal energy, and we can write that will be a change in the internal energy, not a this is not don't take this u as a potential energy function. So that again that will be a probably you will think that this is a potential energy functions. So unfortunately in physics the same symbol can be used in many ways. So when I will write, the danger is there. Suppose, because I have told you that W other cannot be associated with a potential energy function. But now I am going to write this W other as minus delta U internal. But here this U is not a potential energy, that you must remember. That this U is just a symbol for internal energy. Okay, this is a symbol for internal energy and it is not a potential energy function because the energy is lost. That's why I have written it as minus delta U internal. Okay, so what will happen? So in place of, already I have told you that delta, when other forces are present, delta E can be written as W other. So in place of W other, I can write this minus delta U internal. INT means internal, and U is not the potential energy, that is the internal energy, because the internal energy will be load. Load means load, not LOAD load. LOWERED, load means less. So from initial, the final will be less. That's why that negative symbol is used. So I can write this as delta E plus U internal is equal to 0. So you see, again we get the conservation of energy. That implies that conservation of energy is not violated when other forces are present. But you have to take into consideration the internal energy also. Because when you are pulling a box, it will appear that your energy has been lost. But that is, there will be a change in the internal energy, and that if you take into consideration, you will find out that it has not changed. Okay, but then total energy remains conserved. So because delta E is delta K plus delta U plus delta, this delta U is potential energy. That is very important. But the other one is not potential energy, that you must understand. So you cannot express the work done as the change into numbers. Okay, delta U INT is equal to 0. So this brings us the law of conservation of energy. If you understand it, fine. If you don't understand, there is no point worrying about all these things. Only one thing you must understand, that whenever there is a conservative force, it can be expressed in the form of a potential energy function. Whenever a force is non-conservative, you cannot express it as a conservative, in the form of a potential energy function. So naturally, in the next class, a very important thing will come into consideration, that if we are dealing with conservative forces, then what is the relationship between conservative force and the potential energy function with which it is associated, isn't it? Because you see, the potential, just to give you an idea, the gravitational force is Fg is equal to minus mg, and it is associated with a potential energy function which looks like u grave is equal to mgy. So there must be a relationship between the force and the potential energy. That is the question, isn't it? Is there any relationship? And if there is a relationship, what is that? Similarly, if there is an elastic force, it is written as F elastic is equal to minus kx. And it is also associated with a potential energy function. And how the potential energy function is written? It is UEL is equal to half kx square. So is there any relationship between these two things, this elastic function and its associated this elastic force and its associated potential energy? Is there a relationship? If there is a relationship, what is that relationship? This is very crucial, and that will engage us in the next class, isn't it? So just to present a hurried summary of whatever we have learned in this class is that I show you the work done when only gravitational forces are present. I show you the work done when only elastic forces are present. I show you the work done when both the elastic and gravitational forces are present. Also, I show you the work done when elastic, gravitational, and other forces are present. The other forces can be non-conservative forces, and a non-conservative forces can be written as, because non-conservative force, whenever a non-conservative force is present, the final energy is always less than the initial energy. So the total, the work done by other forces can be expressed in the form of change in internal energy. Okay, minus change then delta UINT. But you will not find out that 1 or 2. Okay. So, and that means the law of conservation of energy is a universal law. It can hold good in the presence of all kind of force. to take into consideration all into pictures. So naturally, somebody may find that when other forces are present, probably the law of conservation of energy is violated. No, not like that. Law of conservation of energy is a sacrosanct law. That means it is a sacred law. It is till now it is not found that this law is violated by any situations. Okay, so I hope I should stop it here, and in the next class I will be taking this interesting relationship between conservative force and its associated conservative its associated potential energy function. Okay, so I think I should stop it here, and thank you for your attention. So we'll meet in the next class. Thank you very much.